With annual production exceeding 2.1 million tons, silicone not only serves everyday life, but has also become the backbone of some of the most advanced technology industries on the planet. From hard, brittle blocks of quartz, the material must undergo refining, transformation, reinforcement, and repeated exposure to pressure and high temperatures before being transformed into flexible, durable, and heat-resistant spoons, spatulas, whisks, and baking molds. In today's video, join Factron Process as we step inside the factory to follow the complete journey of turning stone into one of the most important materials in modern life. Each silicone spoon weighs only a few dozen grams, but its journey begins in open-pit quartz mines. In nature, silicon is locked within the structure of silicon dioxide. Manufacturers therefore select high-purity ore in which the silicon dioxide content can reach nearly 99%, with only small amounts of impurities such as iron, aluminum, or calcium. The quality of the ore directly affects furnace efficiency and the purity of the silicon. At some large-scale mines, hydraulic drilling rigs create hundreds of holes approximately 60 feet deep in the rock mass. Explosives are loaded according to a pre-calculated pattern before the area is secured. During a major extraction operation, more than 20,000 tons of rock may be broken apart, after which excavators collect it and dump trucks transport it to the crushing and processing area. The quartz is crushed through multiple stages, screened, and washed to remove soil and rock while producing a particle size suitable for the electric furnace. The processed ore is then blended with coke and appropriate carbon sources. When the temperature exceeds 3,600 degrees Fahrenheit, a complex series of reduction reactions begins. Carbon removes oxygen from silicon dioxide to form carbon monoxide, while gaseous silicon monoxide appears as an intermediate substance. Finally, molten silicon collects at the bottom of the furnace, where it is tapped, cooled, and cast into metal blocks with a purity of approximately 98%. Although it has been separated from the ore, the silicon at this stage remains hard, brittle, and without elastic properties. To become a flexible material, it must enter an entirely different transformation process. After being smelted into metallic silicon, the material continues into a completely different stage. Instead of using extremely high temperatures to separate the ore, engineers begin transforming silicon into silicone through a series of tightly controlled chemical reactions. The silicon blocks are crushed into small particles and introduced into a sealed reaction system, together with methyl chloride and a copper-based catalyst. At temperatures of up to 660 degrees Fahrenheit, the silicon atoms begin bonding with organic groups, forming entirely new intermediate compounds. After several stages of distillation, purification, and hydrolysis, these molecules continue linking together to form long, flexible silicon-oxygen polymer chains. This molecular backbone provides the foundation for all modern types of silicone. While metallurgical silicon resembles a hard and brittle block of metal, silicone polymer has now taken on an entirely different form. It is transparent, soft, and capable of stretching and bending without cracking. However, the material is still not stable enough to become a product suitable for everyday use. The newly formed polymer structure is only the framework of silicone. To withstand thousands of bending cycles, come into contact with food, and operate reliably at temperatures ranging from the freezer to the oven, it still needs additional components in the next stage. Once all the components have blended into a uniform mass, the silicone leaves the mixer and continues toward the rolling system. The silicone polymer is loaded into a high-capacity mixer, where mixing blades continuously press, cut, and turn hundreds of kilograms of material in each batch, so that every component is fully blended. Workers then add additives, the most important of which is reinforcing silica, an ultrafine white powder derived from silicon dioxide, measuring only approximately 20 to 40 nanometers, nearly 2,000 times smaller than a human hair. The silica particles penetrate between the polymer chains, significantly increasing the silicone's strength, tear resistance, and ability to retain its shape after thousands of bending cycles. Colorants, heat stabilizers, and a curing system are then added according to the specific formula of each product. When the mixing process is complete, all the components have blended into a uniform silicone mass, ready to maintain the properties calculated from the original formulation. Each batch of silicone leaving the mixer is immediately transferred to a 2-roll mill. 2 steel rollers with diameters of nearly 600 millimeters begin rotating in opposite directions, forcing the material through a gap only about 1 millimeter wide. The hydraulic system maintains an operating pressure of up to 25 MPa, generating enormous compressive force between the 2 rollers. The dense silicone mass is quickly flattened into a thin sheet before workers fold it and feed it back through the rolling gap. This process is repeated many times until the entire mass achieves the same consistency. Next, a concentrated color block weighing approximately 3 kilograms is placed directly onto the strip of silicone passing through the mill. As it moves through the rolling gap, the color block is broken into extremely small particles and rapidly blended into the silicone. After every rolling pass, the original dark color streaks gradually fade until the entire strip of material has a single uniform color. In addition to adding color, the enormous pressure between the 2 rollers forces any remaining air bubbles out of the silicone while evenly distributing the silica and additives throughout every part of the polymer mass. Workers continuously inspect the material's surface as it leaves the machine, because even a single particle of dust or an uneven color streak can cause the entire batch to be rejected. When the silicone leaves the mill, it has its finished color, a smooth surface, and a uniform structure. This is the ideal condition before the material moves to the forming stage, where it will become highly heat-resistant and elastic silicone products. As soon as the silicone sheet reaches the required thickness and color standard, 2 circular cutting blades made from alloy steel begin rotating at high speed, continuously cutting the material strip into sheets with widths precisely calculated for each product line. Within only a few minutes, hundreds of uniform silicone sheets leave the rolling machine, one after another. Workers quickly separate each sheet and place a PE film approximately 30 micrometers thick between every layer, less than half the thickness of a human hair. Although nearly invisible, this film plays an important role by preventing the silicone from sticking to itself, protecting the surface from dust, and keeping the material stable before it enters the next stage. Stacks of silicone are then transferred to the material dividing area. Here, a cutting system continues dividing hundreds of silicone sheets into individual blanks, sized for each type of product, from spoons and spatulas to baking molds. Each newly cut blank is passed over an electronic scale to check its weight. A deviation of only about 1 gram can alter the amount of silicone introduced into the mold. If there is too little, the material will not fill the mold's thin details. If there is too much, the silicone will overflow and create flash, increasing the processing time required in later stages. It takes only a few minutes for a soft block of silicone to become a kitchen utensil that can be used for many years. The process begins when workers precisely place each silicone blank into a preheated steel mold. From this point, however, the production line no longer follows a single path. Each product enters a mold designed specifically for it. For spoons and spatulas, a stainless steel core or handle is positioned correctly before the hydraulic press closes the mold. Only a few seconds later, the pressure may exceed 1,500 psi, forcing the silicone into every narrow gap and tightly around the metal core, while forming the spoon head, thin edges, and anti-slip ridges. For whisks, the steel wire frame must be held completely stationary. A misalignment of only a few millimeters can cause the entire product to become unbalanced or create a weak point at the connection. Meanwhile, cake molds and baking trays use much larger molds in which the silicone must spread evenly into every deep corner and thin wall without leaving any empty spaces. When the mold is maintained at approximately 400 degrees Fahrenheit, the heat begins activating the curing process. The polymer chains bond tightly together, transforming the silicone from a soft and easily deformed material into a durable, elastic structure capable of withstanding temperatures of up to approximately 450 degrees Fahrenheit. When the press opens, each product is removed with its complete shape and details. When the pressing cycle is complete, the two halves of the steel mold slowly separate, revealing the first silicone products. To separate the product without damaging its shape, workers position a pneumatic air gun close to the edge of the mold. When the trigger is pressed, a high-pressure airflow of approximately 90 psi immediately enters the extremely small gap between the silicone and the steel, breaking the adhesion in an instant. Each spoon, spatula, or whisk handle pops out of the mold without requiring any pulling force. This method protects the thin edges, small corners, and raised details that have just been formed while reducing the demolding time to only 10 seconds for each production cycle. After the product is removed, traces of the pressing process remain clearly visible around its outline. A thin layer of silicone runs along the edge of the product. This is known as flash. It is the material that was forced into the joint between the two mold halves under the strong compression applied during the previous stage. For thin layers of flash, workers can peel them off directly by hand, pulling them away from the product's edge in long strips. Excess material firmly attached around handles, hanging holes, or curved corners is removed with scissors or specialized trimming tools. Each edge is then smoothed and checked again by hand to detect any remaining silicone, ensuring that the surface is flat, soft, and does not cause discomfort during use. Immediately after removal, the products undergo a quick visual inspection by workers. Within only a few seconds, they can identify visible defects such as air bubbles, insufficient material, misaligned metal cores, or silicone that has not completely filled the mold. Products that fail to meet the requirements are removed directly from the production line, while compliant products continue to the stage where excess silicone around the mold edges is processed. After demolding, the products are stable enough to retain their shape, but for many silicone compounds used in household and food contact products, the process is not yet complete. Depending on the formulation and market requirements, the utensils are placed inside a hot air circulation oven for post-curing. The heat continues stabilizing the polymer network and helps remove volatile substances or byproducts remaining after curing. This stage helps control odor, thermal stability, and extractable substance limits. However, not every type of silicone requires post-curing. Some specialized compounds may satisfy the requirements without additional heating. The oven conditions therefore depend on the formulation, thickness, and target market. After leaving the oven, the utensils are allowed to cool in a clean area and are then washed or wiped to remove dust, mold oil, and traces generated during flash trimming. The products are dried, checked for odor, and sorted before being transferred to assembly or identification finishing. After the demolding and flash removal processes are complete, the silicone components are transferred to the assembly area for product finishing. Here, workers manually join the product components one by one. Every connection is carefully aligned so that the parts fit together completely. A deviation of only about 1 millimeter can cause the product to become loose or reduce its durability during use. After assembly, each utensil is gently pulled, twisted, and bent to check the strength of the connection. Products that meet the requirements continue through the laser engraving machine. Within only a few seconds, the laser beam engraves the logo, product code, and identification symbols directly onto the silicone surface without using printing ink. Finally, the product is wiped clean to remove any remaining dust and traces before entering the final quality inspection. Before leaving the factory, every silicone utensil must undergo a final inspection. Camera systems and workers jointly inspect the color, dimensions, surface, and cut edges to detect air bubbles, dents, excess silicone, or misaligned details. For products containing steel cores, the connections are repeatedly pulled and twisted to ensure that they will not loosen during use. Only products that pass all tests are cleaned one final time, packed into bags or boxes, and marked with a batch code and production date. They are then stacked on pallets and transported to the shipping warehouse. From hard quartz particles in the ground, the material has now become safe, durable silicone utensils found in millions of kitchens around the world. Behind every silicone spoon, spatula, or baking mold lies an entire chain of technologies stretching from massive quartz mines and silicon furnaces operating at extreme temperatures to chemical reactions and precision molding lines inside modern factories. From a hard and brittle rock, silicon is extracted, transformed into polymers, reinforced, colored, and finally shaped into the flexible, durable, and heat-resistant kitchenware we use every day. What makes this journey even more remarkable is that it does not end with silicone kitchenware. The same material platform is also found in automobiles, electronics, medical devices, construction, and many other advanced industries. What appears to be a simple material in the kitchen is actually the result of metallurgy, chemistry, and precision manufacturing working together. If you want to continue discovering how familiar products are made inside modern factories, don't forget to like, subscribe to Factron Process, and turn on notifications. See you in the next journey.
Few would imagine that a grass growing in dense clusters deep in the forest could become the foundation of an entire industry, one that supplies more than 80 billion pairs of chopsticks each year, along with countless utensils used in billions of meals worldwide. From bamboo stalks harvested in the forest, the raw material undergoes sorting, splitting, heat treatment, and drying before entering high-speed production lines. There, it is transformed into chopsticks, spoons, forks, and durable cutting boards used in millions of kitchens around the world. So what has turned an ordinary grass into a material that is gradually replacing even wood and plastic? Join Factron Process and discover the answer right now. Bamboo has been part of human life for more than 5,000 years, from the earliest everyday tools to traditional structures across Asia. Remarkably, a type of grass has grown into an industry worth more than $70 billion. With over 1,600 species found across Asia, Africa, and the Americas, bamboo has become one of the world's most important renewable raw materials. What makes bamboo truly remarkable is that it is not a tree, but the largest grass in the world, and some varieties can grow as much as 35 inches in just 24 hours. With its extraordinary growth rate, rapid regeneration, and a fiber structure that is both lightweight and strong, bamboo is increasingly replacing wood and plastic in thousands of products, from household goods and furniture to construction materials. Few would imagine that the chopsticks, spoons, and cutting boards found in everyday kitchens begin with a rigorous selection process deep in the forest. Workers harvest only bamboo culms between 3 and 5 years old, when their cellulose fibers have matured enough to provide the ideal balance of hardness, flexibility, and structural strength. Once marked, each culm is cut close to the ground. This helps prevent the raw material from being crushed or split while preserving the underground rhizome system, allowing new shoots to continue growing. On level terrain, once the bamboo has been felled, workers quickly use machetes or handheld saws to remove every branch along the culm. The bamboo is then inspected and sorted on site according to diameter, straightness, and overall quality before being bundled for transportation. Finally, culms measuring up to 40 feet long are bundled and loaded onto heavy-duty flatbed trucks. Each vehicle can carry between 22 and 33 tons of raw bamboo per trip. From there, convoys leave the forest for collection yards and processing plants, where the transformation of this giant grass into everyday kitchenware truly begins. After arriving at the factory, each bamboo culm is still far too large to be turned into chopsticks, spoons, or cutting boards. It is therefore sent to the primary processing area, where culms measuring between 15 and 30 feet long are cut into standardized sections. Each 30-foot culm is placed on a conveyor and fed directly into an automatic bandsaw. A high-speed alloy blade slices cleanly through the bamboo, cutting it into sections of uniform length. Every cut is carefully calculated to maximize material yield and keep waste to an absolute minimum. But cutting is only the beginning. The bamboo sections are immediately fed into a bamboo splitting machine, where a set of steel blades drives outward from the core, dividing each section into 8 to 16 evenly sized strips in just seconds. Remarkably, the machine hardly needs to cut across the material's fibers. Instead, it takes advantage of the cellulose fibers running lengthwise along the comb, splitting the bamboo along its natural grain. This not only speeds up the process, but also preserves nearly all of the material's inherent strength. Finally, the strips move into a double-sided planer, which removes the silica-rich green outer skin and the softer inner layer. Only the densest, hardest, and strongest bamboo fibers are retained for the production of kitchenware. Freshly split bamboo strips still contain moisture, sugar, and starch, elements that can encourage mold, attract insects, and cause deformation. To remove them, the strips are stacked on racks and placed in boiling tanks or steam chambers for 2 to 4 hours at temperatures between 194 and 200 degrees Fahrenheit. The heat penetrates deep into the fibers, removing most of the remaining organic compounds. Immediately afterward, the bamboo is transferred to a kiln dryer. A continuous flow of hot air passes through the gaps between the strips, gradually reducing their moisture content to about 8 to 12%. This stabilizes the bamboo, minimizes shrinkage, and gives it the durability required for the next production stages, where it will be transformed into chopsticks, spoons, straws, or cutting boards. Once stabilized, the bamboo strips officially enter the chopstick production line, beginning with blank cutting. A conveyor continuously feeds each strip into an automatic cutting machine. As soon as a sensor detects the correct position, an alloy saw blade drops and cuts the bamboo into blanks, measuring approximately 8 to 9 inches long. In just 1 hour, the line can produce nearly 18,000 blanks with almost identical dimensions. Thanks to this precision, the blanks move directly to the shaping stage without requiring any additional trimming, keeping the production line running continuously while minimizing material waste. The freshly cut bamboo blanks are still little more than small square strips with sharp edges. Only after passing through the shaping line do they begin to take on the familiar appearance of finished chopsticks. First, the blanks are continuously fed into a chopstick shaping machine. Inside, multiple blades and cutting rollers operate simultaneously, trimming the edges, smoothing the bodies, and beveling both ends according to programmed dimensions. Within seconds, the rough bamboo blanks are transformed into straight, evenly tapered, and well-balanced chopsticks. Immediately afterward, they pass through a multi-head sanding machine. Continuously rotating abrasive belts smooth the entire surface, removing tiny splinters and any remaining scratches. This stage not only creates a comfortable grip, but also ensures that the chopsticks are safe for direct contact with food. For decoration, the chopsticks are aligned vertically in a holding rack, with their ends positioned at the same height. The entire group is then lowered by machine into a bath of food contact-safe paint or coating. The liquid is continuously pumped and circulated to maintain an even consistency, while each chopstick is dipped to a controlled depth, creating a clean, uniform band of color. As the rack rises, excess coating drains back into the bath before the chopsticks move to the drying area. This method allows dozens of chopsticks to be decorated at once, with nearly identical color coverage and coating length. At this stage, the chopsticks are fully shaped, but one final step remains before they reach the dining table. The entire batch passes through a sterilization chamber, reducing the risk of microbial contamination while preserving the bamboo's natural color. The chopsticks then move directly to an automatic packaging machine. Operating at approximately 300 pairs per minute, the system counts, aligns, wraps, and heat seals each pair. Just minutes after entering the production line as rough bamboo strips, they emerge as fully packaged chopsticks, ready for shipment to restaurants, supermarkets, and markets around the world. Unlike chopsticks or straws, bamboo spoons and forks feature a variety of curves and dimensions, requiring exceptional precision from the very first cut. Once treated and dried, each bamboo strip is placed on the work table of a CNC machine, where mechanical clamps hold the material firmly in place to eliminate vibration during cutting. When the programmed cycle begins, a carbide cutting tool spins at speeds exceeding 20,000 revolutions per minute. However, the spoon's bowl and the product's smooth curves are not formed at this stage. The bamboo blanks are transferred to a heated molding press, where the upper and lower dies close under intense pressure. Heat and force work together to press the material into its designed shape. Within just a few dozen seconds, the bowl of the spoon, the curvature of the fork, and the transitional surfaces are formed consistently, without cracking the bamboo or damaging its fiber structure. By combining CNC cutting with heated molding, each spoon or fork leaves the production line with an almost complete shape, ready for sanding and final finishing. After shaping, each product has reached its final form, but it is not yet ready for use. Tiny cutting marks and any remaining sharp edges must be removed before the finishing stage. The products pass one by one through a profile milling machine, which precisely refines the spoon bowls, fork edges, and the transition points between the handles and bodies. Immediately afterward, they enter a multi-stage sanding system. High-speed abrasive rollers continuously remove extremely thin layers of bamboo fiber without altering the carefully machined shape. After surface finishing, every product must pass a series of tests to ensure durability and safety for direct contact with food. Along the inspection line, workers randomly select samples and boil them in hot water to evaluate heat resistance, coating stability, and any signs of warping or cracking after exposure to high temperatures. For products such as spoons, forks, and chopsticks, many factories also conduct bending and load tests. These trials simulate real-world use, measuring flexibility while revealing hidden cracks within the bamboo fibers. Only after passing every inspection can the products move to the packaging line. There, automated systems sort the items, arrange them into sets, apply labels, and seal each package before shipment. Every carton must meet strict quality standards, completing the transformation of natural bamboo combs into strong, durable kitchen utensils, ready to serve millions of households around the world. Unlike chopsticks or spoons, which are machined from a single strip of bamboo, cutting boards must withstand thousands of heavy chops and repeated impacts throughout their service life. That is why their durability is determined from the very first stages of production. After treatment and drying, the bamboo strips are sorted by size and grain direction, coated with food-safe adhesive, and arranged tightly together before entering a hydraulic hot press. At temperatures of approximately 250 to 300 degrees Celsius and pressures reaching 2,000 to 3,000 psi, the strips bond into a dense solid panel designed to resist warping, cracking, and separation during use. The bamboo panel then moves to a CNC machine, where carbide cutting tools trim it to precise dimensions, round the corners, and carve drainage grooves or handles depending on the design. Finally, the board passes through a multi-stage sanding system to smooth the entire surface before receiving a food-grade oil finish. This protective layer improves moisture resistance, enhances the bamboo's natural grain, and extends the product's lifespan. In just a few production stages, separate bamboo strips are transformed into a strong, durable cutting board, built to serve in the kitchen for years. Rather than using large, thick bamboo combs, factories often select slender stems measuring only about 0.5 inch in diameter to create a product capable of replacing hundreds of plastic straws over its lifetime. After being treated to remove dirt and impurities, the slender bamboo stems enter an automatic cutting machine. A positioning system holds each stem securely before a saw blade divides it into sections approximately 8 inches long, the standard size for most beverages. The bamboo sections are then arranged evenly on trays and placed inside an industrial drying kiln at approximately 175 degrees for several hours. Continuously circulating hot air reduces the moisture content to around 8%, helping prevent warping, cracking, and mold growth during use. Once stabilized, each section moves into the internal cleaning and polishing stage. A long drill bit or abrasive rod passes through the naturally hollow channel, removing internal nodes, loose fibers, and any remaining rough areas. At the same time, both ends are ground and rounded to eliminate sharp edges, while the outer surface is polished to achieve the required smoothness. Finally, The straws are thoroughly washed, sterilized, and dried one last time before being inspected, sorted, and packaged. From a slender bamboo stem, a strong and durable drinking straw, designed to be reused again and again, is now complete. But bamboo is not the most fascinating material in the kitchen. Next, let's see how quartz sand is transformed into flexible, heat-resistant silicone utensils.